Yeah, last time we started discussing curvature of a curve. So we learned yep, three-dimensional space curves, how to find the curvature, how to find the curveness. So curveness is the measurement of the turning or measurement of how fast that curve turns in the space. Yeah, it's a measurement. Yeah. So we know that this is the fundamental, this is the fundamental definition of the curvature. The rate of change of unit tangent vector along the path. Yeah, so you have to take the magnitude, magnitude of this. This is a scalar. Yeah, the rate of change of unit tangent vector along the path is given by the curvature of the path, right? So that can be expressed in terms of t. You can change variables, right? So you know how to do that using chain rule. And curvature of a straight line is zero. Yeah, that makes sense. Curvature of a circle has, it is constant at each point on the circle. Yeah, it is constant. 1 over radius. Yeah, curvature can be expressed in if you deal with physics problems. We are dealing with velocity of a particle, velocity acceleration, right? So you can express curvature in terms of velocity as well as the acceleration of the particle. The particle is moving along a space curve, 3 dimensions, or in 3 dimensional space, or 2 dimensional space. Doesn't matter. Yeah, I think 3 dimension makes sense, but here 3 dimensions you can compute this cross product. No, yeah. So this makes sense for 3 dimensions. Yeah. So mhm, the helix. Yeah, we found that. Yeah. And if you have 2 dimensional curve, we can obtain an equation for curvature, right? Using our fundamental, using this AI expression. Yeah. So this is the curvature of a 2 dimensional curve. Yeah. So this is the 2 dimensional curve function, right? So this is the curvature varies at each point. Yeah. So there's a maximum curvature at this. Yeah. Curviness is very high, higher than any other point. And then, and then we define another unit vector, which is called a unit normal, principal unit normal vector. So this is perpendicular to the unit tangent vector, right? So actually, so here we go. Yep. So we know that the unit tangent vector is always, its direction. Yeah. So in the direction of the tangent, so this direction, and the other newly defined, vector, principal unit normal vector is perpendicular to this unit tangent vector, and it points to the inside of the curve. Yeah, curve inside of the curve. All right, so so I think I didn't have time to discuss this. Yeah, last time we were talking about components we can find if you discuss the physics problem here, right? So we can find, so let's assume a particle is moving along a space curve, along a path, 3 dimensions, right? In 3-dimensional space. Yeah, it has velocity as well as the acceleration, right? So you can find the speed of the particle by taking the magnitude. Magnitude of the velocity is the speed, yeah. The rate of change of distance, yeah. Rate of change of distance is the speed, yep. So then we can find tangential and the unit and the normal component of accelerations of a particle. So I think I have discussed this proof, I think, yeah. So this one here, yeah. So this is the tangential component of the acceleration of a particle. If a particle is moving along a certain space curve, right, in 2 or 3 dimensions, right? And this one is the normal component of the acceleration. So let's discuss a small example. Right? So let's say a particle is rotating around this circular path. So if you have, this is centered at the origin, and the radius is uppercase R, and that particle is moving with this angular velocity along this circular path, right? And let's find the, I think A-levels, in physics, I think, they discuss circular motions, motions, yeah. So they find tangential acceleration as well as the normal acceleration. If a particle is moving along this circular path. So actually this is a 2-dimensional curve. Yeah. So this particle is moving with this angular velocity omega. Then what is the normal component of acceleration and tangential component of acceleration? Let's use this. To find the tangential component of this part of acceleration, so we had to find this term. Okay, so first r is given, then you can differentiate. So so this particle depends on the time t represents time, right? So you differentiate this once, then you get velocity. Okay, this is velocity. And if you take the magnitude of that velocity, you get speed at a given time t, right? Let's find the magnitude of this vector. What is the magnitude? Square root of this one squared plus this one squared, which is r omega. Yeah, that is ds by dt. The rate of change of distance, yep, is the speed, magnitude of velocity. Yep. So this there is no t term, or that means this speed does not depend on the time, right? So when you differentiate this one again, what happened to this term? This term becomes 0. Then there is no tangential component of acceleration for circular motion. Right? Tangential. There is no tangential component of acceleration, but it has, I think, unit component, normal component. Let's find that. You need velocity as well as the acceleration to find the normal component of this. yes, this this circular motion. Yeah. So let's find the acceleration. Yes. No, yeah, you need acceleration. And yeah, yes, that. Yeah, this one. Ah, yeah, this one. This is yeah, normal component of acceleration is same with yeah, kappa. You know the curvature of a circle. So radius is r. The curvature at any point of this curve is 1 over r. Yeah, it is known 1 over r. And here you know the speed. Speed is r omega. Yeah, then you can find the normal component of the acceleration, which is 1 over r times r squared omega squared, which is r omega squared. So this is the if a particle is moving along this circular along this circular path with this with this constant velocity, so there is only acceleration component. Yeah, so it is which is normal component. So r omega squared. I think in physics, I think you take this component. Yeah, if particle is moving around the circular path. Yeah, so that makes sense. This is that is all right. Another example. Yep. So this time our path is parabolic, right? Yeah. So this is our path, like this, right? So you are given the parametric equation. So this is parametric equation here. The path depends on only one variable, t. Yep, so you can find the velocity by differentiating this as well as the acceleration. Differentiate this twice. Yep. And you can find tangential, unit tangent as well as unit normal. So then you know acceleration vector. So if you want to find the tangential component, just take the dot product. Dot product between acceleration and the unit tangent. That's give the that that gives you the tangential component of the acceleration. If you want to find the normal component of the acceleration, take the dot product of this acceleration with this, and that gives you this is the normal component of the acceleration. Yeah. Anyways, here, because here you have acceleration straight away. Earlier we didn't calculate acceleration. You can calculate acceleration. You can differentiate this one again. Then find the tangential vector and normal unit tangential and unit normal. Then take the product. We can find each component, tangential component as well as the normal component. Yeah. That makes sense. Yeah. Any questions? Yep. Before talking about the curvature, we should talk about the smoothness of the path. So the path should be smooth. That means you don't have any these kind of edges and these kind of cusp, right? You don't have anything like this. Have smooth curve like this, smooth, very smooth. You don't have rough, yeah. So edge sharp edges like this. So at this point, yeah, it is the curve is not differentiable. So this, yeah, first derivative should be continuous and non-zero, right? If you want to define a curvature of a path or curve, space curve, so we have to say, yeah, we have to say at the beginning. Then we can define that definition. Curvature is equal to rate of change of the unit tangent vector along the curve S. Yeah, S is along the curve S. Yeah. And you can change variable. If you like to change this variable S to T, yeah, you can use chain rule. Yeah, you know how to do that. Yeah. So yeah, that I should have mentioned at the beginning. Then so then you can define the curvature. Yeah. So we define unit tangent and what is the other one? Unit norm. Unit norm vector. So if you take the cross product of unit tangent and unit norm, what do you get? A vector which is perpendicular to both t and n, right? B. So we define this vector which is called unit binormal vector, right? Right? So how do you define that? By taking the cross product of unit tangent as well as the unit normal vector. So when you take the cross product of unit tangent and normal, you get a vector which is perpendicular to plane of t and n. So this t and n b, they are moving frame. So these are unique. So you can find the magnitude of this one. So what is the magnitude? Yeah, magnitude is, yeah, let's find the magnitude of B. Magnitude of this, magnitude of T is, 1. Magnitude of N is 1. Sine of the angle between these two is 90. Sine of 90 is 1. And magnitude of unit vector which is 1. That means this one also a unit vector. B, uppercase B, this vector is also a unit vector. So we call it unit binormal vector, right? Unit binormal. So when the particle is moving along this path, so this frame is also moving. This frame is also moving. You get different NTB at different points. So this, okay. So this is attached to this curve. This is this frame. B and TBN frame is attached to this curve, right? So this is used to calculate curvature and torsion of a curve. Torsion means twisting. ඇම්බරීම කියන්නේ curvature කියන්නේ වක්‍රතාවය. ඔන්න වක්‍රතාවය curvature. මේකේ වක්‍රතාවය කියන්නේ curvature. Torsion කියන්නේ ඇම්බරෙන twisting. So to measure those curvature and twisting of the curve, we use these three vectors. These are unit vectors which are moving along this path. If a particle is moving, then these three vectors are moving accordingly. Okay. So this TNB frame is used to track the motion of robot arms in robotics. Yeah, so those kind of thing. Yep. So, and this frame is also called what does, yeah, this frame is also called, let me, yeah, write that down. Yeah, Fresnel, that's the brand name. Yeah, so Fresnel, the French mathematician, Fresnel, and yeah, so, so so, yeah, frame, TBN or Fresnel, so frame, yeah. So two French yeah, mathematicians, they found this frame, and it is a moving frame attached to this curve. Yeah. Okay, so let's see how do we find the torsion of this curve. We found curvature and वक्रता. We measure how quickly that curve, how fast this curve turning, how fast this curve turns. वक्रता. Torsion, yeah, torsion. Let's see how to find the torsion of the curve. Yep. Yeah. Yeah, they are yeah, so you need, yeah, orthonormal basis. So they are orthogonal here 90 90 90, and unit normals, unit vectors. Yeah, this is a orthogonal basis, yeah, of frame. Yeah, I had a video. So I had a video how the particles are. Yep. Yeah, let me. What was GeoBra? This is T. Yeah, let me TN TPL TNV frame frame GeoBra yeah, GeoBra TBN frame. Yeah. So this is this link. Yeah. Look at this. Uh-huh. I will send this. Yeah, this is tangent. Yeah, tangent, normal, unit normal, and B, the cross product of T and N, which is B. Yeah. So when you change this parameter value, yes, this is the relationship. Yes. When you change this parameter, look at this TB, yeah, TBN frame moves along the curve. Yeah. And this is the plane of, yeah, this is another one, osculating, yeah, osculating plane of T and N is called osculating plane. So look at that plane changes, how that plane changes according to this parameter value. Alright, it's moving, yeah. So I will send this link to you. I will send this copy. Yeah, everybody, yeah, so yes. Yeah, so let me pause the video, the session. Okay, why do we discuss, why do we need this vector B, uppercase B, unit binomial vector? So why? So to measure the torsion of the curve torsion of the curve. Here we go. So this is n, t, tangent, unit tangent, normal, and torsion එක කියන්නේ මේ plane එක ඇතුළට ඇඹරෙනවද එළියට යනවද අන්න ඒක තමයි torsion. මේක තමයි oscillate plane එක, plane of n and t. The twisting into this plane or out of the plane. So we have to measure that. Yeah. So yeah. So let me discuss this. Yep. So so let me discuss the properties of this unit binomial vector. Right. So use this. Yeah. Right. This vector is orthogonal perpendicular to both t and this vector. Let's see how, right? Okay, what is the definition? B is the cross product of t and b, right? Torsion व्यवस्था වන්දන් ඇම්බරීමද කොහෙද torsion කියන්නේ ඇම්බරෙන එක. ඒ plane එකට TN plane එකේ ඇතුළට යනවාද එළියට එනවාද අන්න ඒක measure කරන්න. මේ හදන්න torsion එක. වක්‍රතාවය කියන්නේ එහෙම T මේක තමයි N එක මෙන්න මේක T මේක measure කරන වක්‍රතාවය torsion කියන්නේ මෙහෙම ගිහිල්ලා මේ plane එකෙන් උඩට එන්න පුළුවන්. මෙහෙම එන්න පුළුවන් නැත්නම් යටට යන්න පුළුවන් මේක check කරන්න. 3 dimension නේ. අපි වැඩ කරන්නේ 3 dimensions වලනේ නේද? අන්න ඒකට. ඇම්බර් වෙනවා කියලා twisting into the plane or from the plane. Yeah, so let me discuss it. So dB by dt ds is orthogonal or perpendicular to both t and let's see how. Yeah, we know that b is equal to cross product of t and b. Let's differentiate b with respect to s. This is this is vector product. So then so this is, I think we know this one. The differentiation of this first one with respect to s cross other vector plus this one cross differentiation of other vector. So we know that n and these two are parallel. Why? Let me check. These two are parallel. Yes. D. Why is that? According to the definition of. Here we go. N is parallel to dt by ds. So n is parallel to dt by ds. N is parallel to dt by ds. Then this is 0. This is 0. Then we get over this term. So that means dB by ds is perpendicular to t and dn by ds, right? And this one also perpendicular to b and t. Why? No, this one is also perpendicular to b. Why? So magnitude is 1. Magnitude squared is also 1. You can use this one is same with dot product, right? Dot product. So this is same with b dot b, right? B dot b is equal to magnitude of b squared, right? So differentiate. When you differentiate this with respect to s, so right hand side differentiation of ds, this becomes 0. So this is equal to b times db over ds. 2, there's a 2 here, you can ignore because it is non-zero. Then B and DS are perpendicular. B and DS are perpendicular. Orthogonal, right? Orthogonal. And we know that DB, oh, it's confusing. DB by DS is perpendicular to T. Yeah, so this makes sense. So dB by ds is a perpendicular to both B and T. Yeah, that makes sense. Yeah. So yeah, perpendicular to both B and T. Then this is parallel to what? So because this one is perpendicular to both B and T, perpendicular to B and T, then this one is parallel to which one? Because this dB by ds is perpendicular to both T and B, then which is parallel to N. Yeah. N. So dB by ds is perpendicular to T as well as B, then dB by ds is parallel to N. Yeah, so here we go. So then we can define the torsion. Yeah, this is the torsion. Yeah, torsion of the curve. Yeah, tau is the torsion. Yeah, so there we go. Yeah, tau is the torsion. Here we go. So they define negative tau. Yeah, that's yeah. So yeah, so here look at this. The plane span by T and N is called the osculate plane. As I said before, yeah, this is the osculate plane. Yeah, spanning of N and T. Yep. So you can using N and T, you can write any point on this curve on this plane, right? So that's why we say, yeah, this plane is spanned by T and N, right? So, all right, okay, it's called obsculate. Yeah, they give a name. The rate at which the curve determined by are twist in or out of the obsculate plane is measured by this. කෙනෙවන් කිව්වේ so මේ ප්ලේන් එකේ ඇතුළට හරි උඩට යන මෙෂර්මන්ට් එක බලන්න තමයි ටෝෂන් එක එව්වේ. අරක බලන්නේ other one. So this is curvature. මේ ඇතුළේ curve එක මෙහෙනේ ඇතුළේ curvature. උඩට යන පහළට යන මේ curve එකට hit වෙන curve එකකින් නෑ plane එකට hit වෙන හිට් වෙලා යටට යන එක්කෝ ඒක ප්ලේන් එකේ උඩට ඩිං ගාලා රොකට් එකක් වගේ යන අන්න ඒක බලන්න ටෝෂන් එක ටව් ඕන වෙන්නේ ටව්. Make sense? That's why we discuss B here. So for that we need B. So here we have B. So this is B, vector B is perpendicular to this plane, NT plane. So this is B. So yeah. Does that make sense? So let's see, how do we compute this torsion? How do we measure the torsion of the curve? All right. So you are given a curve. Here, this is famous helix curve. Here, this is your famous helix curve. Right? Okay. Yeah, so then you can find the unit tangent, unit normal. Right? You know how to find. unit tangent and normal, and you can find B as well by taking the cross product. Yeah. So torsion with respect to T. There's a way one guy is asking, yeah, obsculate circle. What's the meaning of obsculate circle? Circle, plane. Take, yeah, circle. You don't need take. Yeah. So this plane is spanned by n and t. So using this n and t, this is like your x and y axis. So these are unit vectors, right? So remember when I talk about two dimensions, x and y, so we had two unit vectors along ox, which is I, and other one is j, right? So similar to that, you have two vectors, perpendicular vectors like this. Then you have this infinite plane here. This is plane of oxy. So this is plane of t and n. Yeah. So using these two vectors, you can write any point on the plane, right? So using n and t, you can write any point on the plane. Yeah? So this is plane of t and n. It is called obsculating plane, right? Or you can say, yeah, plane. Yeah, just say plane. So according to that example I gave you, yeah, so this is plane of T and N. So they put osculate circle, right? So because this is our famous helix curve. So this circle is rotating around this spiral osculate. Yeah, that's why they mention this is a circle. Yeah. So this is the tangent and normal. Yeah, this is rotating around this. Yeah. So when you change here, nicely rotating. Also, okay, okay. Yeah, you can convert this to in terms of t. Yeah, if you want. Yeah, by using chain rule, you can convert if you want. But so here I don't convert that to in terms of t. Yeah. Yep. So yeah, they convert here. Here we go. Here by using chain rule, can convert here dB by ds. Yeah, converting this into terms of t. Here. Look at this. So because b is expressed in terms of t here, not in terms of s. So here we need b. We have to write b in terms of s to calculate torsion. But in this problem, yeah, when you find t and s in terms of t, parameter t, and when you take the cross product, yeah, again you get in terms of t, b expressed in terms, in terms of t. So how do you compute this? Yeah, you have to use chain rule. Yeah, chain rule. And this is the speed. Yeah, no magnitude of speed, velocity. Yeah. So b in terms of t, then you can find the first derivative of b by differentiating this with respect to t. Yeah. And speed. Do we know speed? Yeah, I think we know speed of this famous curve. Yeah, helix curve. Yeah. What is the speed? I think we found speed. I think. Yeah, speed is what was that? So you have to check that one, I think, again. Yep. So then we have this in terms of t here, in terms of t, dB by ds expressed in terms of t. by taking the dot product, that is the definition. Yes, this is the definition. Yeah, d by ds. Yeah, so if you want to find isolate tau, you have to take that product both sides n. So n dot n is equal to 1 because n is a unit vector, n squared. Magnitude of n squared is 1. Yeah. So then you can isolate. Yeah, you can solve for tau. Solve for tau if you want to isolate this tau in the equation. Yeah. So that's why they consider taking the dot product with it. Yeah. So this is the torsion of the famous helix function. Yeah. You can remember අර ප්ලේන් එකේ ඇතුළට හරි උඩට ඇවරෙන එක තමයි මේ. So does this make sense? Any question?